Welcome to yet another movie on classical mechanics. I am Jos Thijssen and I teach classical mechanics to the second year students applied physics at Delft University. In a previous movie I have derived the principle of stationary action from D'Alembert's principle, and in this movie I will start from that principle of the action which should be stationary for the mechanical path, and I will formulate that in terms of generalized coordinates, and I will derive the equations of motion from that also in generalized coordinates, and those are the famous Lagrange equations of motion, or Euler-Lagrange equations. I hope the movie will be helpful for you. In a previous movie I have explained how the Lagrangian formalism works. In fact, in that movie I started from D'Alembert's principle, which is satisfied by mechanical paths, eventually satisfying some constraints that are imposed on them. And the conclusion was that if we look at the mechanical path of a particle moving in a conservative potential field from a position R1 at T1 to position R2 at T2, that is a stationary solution of the action, and the action is defined as follows. We use for that a letter S, and the S is the integral from the starting time to the final time of L, and that is an integral over the time, and the L is a function of the positions and of the velocities of the particles, and it can also be written as T minus V dt, where the dt is the kinetic energy and V is the potential. And it's important to realize that so the statement is that the path should be a stationary solution of the action. So if you have a path that satisfies the equation of motion, so it's a correct path, then if I perturb the path a little bit, then to first order the action does not change, and the path and all its variations should be compliant with all the constraints. And we know that for a path which is compliant with the constraints, we can write all the positions of the particles as a function of time in the following form. We can write them as an Ri. There is a part of the time dependence which is given by the so-called generalized coordinates. They are Qj, and then there may be or may not be an explicit time dependence. So the Qj are the generalized coordinates, and they themselves depend on time. Now it will be clear that given the fact that the Ri depend on the generalized coordinates, I can write the Lagrangian L, which is a function of all the Ri's, of all the Ri dots, and perhaps depends explicitly on time. It's clear from this that we can replace this by an L that depends on the Qj, the Qj dot, and perhaps the time. And so also for an action that is expressed in terms of an L that depends on the generalized coordinates, we should still find a stationary solution. And so that is in fact the aim of this movie, is to derive equations of motion in terms of generalized coordinates from this principle that the action should be stationary. So we can summarize the task as follows. We have a action, we have an action which is defined as an integral over the Lagrangian, which depends on generalized coordinates. Now we perturb the path which satisfies the equations of motion, because that's the path we are trying to find. We try to find the path which satisfies the equations of motion, and for that path it should hold that if we perturb it slightly, then the change that is caused in the action, so the delta S, should be 0 to first order in the delta QJs. And now I need to be a bit more specific, because we cannot use any perturbation. First of all, the delta QJs should be small, obviously, but there is an additional requirement, and that is the delta QJs should be 0 at the first time, at the initial time t1, and also at the final time. And what this means is that all the paths I want to consider are paths which have the same starting and the same end point. So if I can perturb a path, but I cannot change its initial and its final point. And so for these we need to work out this condition, namely that delta S is 0 to first order in J, in delta QJ. And in order to proceed, we should do a Taylor expansion in these delta QJs. And here is this Taylor expansion. So we expand in the delta QJ and in the delta Q dot J. So this, of course, we first get a 0th order term. That's the unperturbed Lagrangian, which is cancelled by the second one, so we can leave out the 0th order term. The first order term gives us two contributions, one from the delta QJ, which has this form. It's the L dQJ multiplied by delta QJ, and then the second one is due to the delta QJ dot. It gives me delta L, delta Q dot J, delta Q dot J. And now we should realize ourselves that all these delta Q's, they are small but arbitrary, and it would be convenient to have only a delta QJ in both terms, but here we have a delta QJ dot. And so we would like to remove the dot from there, and we can do that using partial integration. So here we have performed the partial integration for the second term. So the first term is just copied from this expression to this one. Nothing has changed there. For the second term, we want to move this time derivative towards this first term, and then we get one integrated term where the time derivative here has disappeared. And that is an important point, because we had made the assumption in the beginning, or the requirement, that the delta Q vanishes when we evaluate it at t1 or t2. And that's precisely what we need to do in this integrated term. It has to be evaluated at t1 and t2. In both cases, all the delta QJs vanish, and so this term will not play any role. And then finally we have the integral with the minus sign, characteristic for partial integration, and we have moved the time derivative from this term to this term, so we get a ddt before the dl dq dot j. And so if we rewrite the expression now, we see that I obviously get an integral from t1 to t2. I have a sum over j. Now both these terms, they carry a delta qj, so I can put that delta qj now outside of brackets. And then inside the brackets I have a dl dqj minus d dt. This is a full derivative, and then we have dl partial derivative with respect to q dot j. And now we note the following. The delta qj are small but arbitrary. So what I can do is take all the delta qj's except for one equal to 0. So what I can do is take qj is not 0, and all the qk's where k is not equal to j, I take those 0. And then I see that because this qj, I can also take the qj non-zero only at one very small interval in time during t1 and t2. So this qj, of course it depends on time, so let me assume that it has this function, this value, this form. Then obviously from the integral it picks out only this dl dqj minus ddt dl dqj dot at that particular time, which is a time in between t1 and t2. And I can take this time to be anywhere because the delta q are small but arbitrary. And so I conclude that for each j and each time, this term in parentheses, in the big brackets, should vanish. And so the conclusion is, and that is a very important conclusion, the conclusion is that ddt dl dqj dot is equal to dl dqj, and these equations are known as the Lagrange equations of motion. Sometimes people call them also Euler-Lagrange equations. And so they form one of the central results of analytical mechanics, and in particular they allow us to find the solution to the motion of complicated systems with a minimum of effort. So that was the movie in which I derived the Lagrange equations of motion. Now, of course, you can only appreciate the value of this result when you have seen different examples, and all the books on classical mechanics, lecture notes, they all abound with exercises, with examples where you use these equations, and I hope to work out also one or two in additional movies. I hope it was helpful for you.